All right, so it's a pleasure to have Raphael, who in addition to, with Alice being the lead organizer of the conference, has kindly offered to tell us about entanglement wedges for gravitating regions.
Thanks, Daniel. And I'd like to complain to the organizers for making us come in so early. Completely uncivilized. I'm sorry about that. Yeah, so I want to tell you about some work with Jeff Pennington. This is probably the 10th paper at this workshop that involves Jeff in some way. Let me start by reminding you of sort of a little bit of history. I think the Ryu Takeyanagi paper came out maybe in 2006. In a way, it marked the beginning of when we were starting to use ADS-CFT to learn something about quantum gravity rather than learn something about strongly coupled field theories. That's a bit of an exaggeration, but I think it really was a turning point. This was a prescription originally for computing the entropy of some CFT subregion in terms of the area of some minimal surface. And in this original paper, as in most of this talk, the focus was on static situations, more precisely time reversal symmetric configurations, where you really just look at one time slice and you search for a minimal area. This was generalized to the time-dependent setting by Hubeni, Rangamani, and Takeyanagi a year later. And then the inclusion of quantum corrections, again, first in the static setting, was by Faulkner, Lukowitz, and Maldacena. So they said, well, if you really want to compute the order 1 corrections rather than just order 1 over n squared leading contribution to the entropy, you have to include the entropy of matter in the bulk as well as the area of the surface. And then finally, Engelhardt and Wall gave what I'll call the quantum extremal surface prescription, which is a covariant version of this, and also something that is supposed to hold to all orders in an expansion, in a perturbative expansion in G Newton H bar. So what you're supposed to do, of course, is to find a stationary generalized entropy surface in the bulk that's homologous to the boundary region. And if there are multiple such surfaces, you find the one that has the smallest generalized entropy. Okay, so initially this was all, I think the perception was this is all about computing entropy of the boundary conformal field theory. But I think maybe the more important thing that came out of this is that it also gives the answer to a much more general question. And the connection between that, of course, was explored in various papers by Daniel Harlow and collaborators, for example. It answers the question of which part of the bulk can you actually describe if you're given access to a certain part of the boundary. There's this problem of subregion duality, which I'm proud to, I think, have maybe articulated first, though answered completely wrong. And I think Aaron Wall was maybe among the first people who said we should really be looking at the homology region that's defined by this quantum extremal surface. So everything in between the boundary and that quantum extremal surface is what we can describe. And describe means in this fascinating sense of operator quantum error correction that was first spelled out by Almeri, Dahl, and Harlow. So if I have a local operator here in the bulk, then I can find some operator on the boundary, region B, which when acting on states in the code subspace, meaning, for example, states in which the geometry is not dramatically different from this one, it will have the same effect as this local bulk operator. Okay. So that's the end of the history lesson. So now I want to do some alternate history. I want to stress that this could have been discovered in some other universe or whatever by some other physics civilization before ADS-CFT. I think in our perception, it's very much part of ADS-CFT. It's sort of something we view as part of the dictionary, maybe. But I think that's kind of the wrong way of thinking about it. It could have been discovered the same way that Gibbons and Hawking discovered a way of computing the thermal entropy, or the coarse-grained entropy of a black hole. You could think of it as a refinement that allows you to compute the fine-grained entropy. This is not how Gibbons and Hawking maybe thought about it, but the attitude would be that you assume that there exists some quantum gravity theory that has something to do with your boundary, and then use the gravitational path integral to either compute the thermal entropy by putting the boundary on a thermal circle, or you think of Ryutake-Yanagi as a clever way of using the gravitational path integral to compute Renyi entropies and taking an analytic continuation to n equals 1. And if you think of it that way, then the same way that Gibbons and Hawking guessed in the 70s that you can compute some kind of entropy of whatever theory, they didn't have a theory, by doing this Euclidean path integral, you could have guessed that Ryutake-Yanagi is the correct way of computing the microcanonical entropy of some unknown theory. We need not have had ADS-CFT at that point. You didn't have to have a theory in your hands. In fact, it could have helped us in that alternate history to figure out ADS-CFT. You know, you learn something about the structure of the entropy and so on, and eventually you realize, duh, it's a CFT.
So this actually was the attitude of Lukowitz and Maldacena, right, in their paper, which at the time I thought they were being very weird. Why were, they called it generalized entropy, gravitational entropy, and they ignored ADS-CFT until the last possible moment.
Exactly. Yeah. So, and I thought I had them on this slide, but I didn't. I really apologize for that. Yeah. This is exactly what's, so if you look at the, thank you, Daniel. So if you look at the proof of the Ryutake-Yanagi formula by Lukowitz and Maldacena, it doesn't use ADS-CFT. It's just the gravitational path integral. And what I just said, right? You're using the gravitational path integral to evaluate the Renyi entropies. And then you show that taking the limit as n goes to 1, that calculation reduces to the Ryutake-Yanagi prescription, or FLM. So the lesson that I want to stress here is that this is one of those miracles of semi-classical gravity or of the gravitational path integral. It's not in itself about ADS-CFT. Of course, it's great to have ADS-CFT because then we can check and see that, yes, it gives us the right answer. In some cases, you know how to compute entropies in the CFT, then you can check that it works. But that's an independent check. Now, nevertheless, and despite the efforts of Aitor and Juan, I think we kept thinking of this as an ADS thing, in part because there aren't a whole lot of non-trivial minimal surfaces or quantum extremal surfaces in spacetimes other than asymptotically ADS spacetimes. Like you can't go to the Sitter space and anchor some minimal surface on the future boundary. They don't exist. Even in flat space, you can't. Asymptotically flat space. But that's where islands come into the story. So islands are these completely isolated places where the minimal surface or the quantum extremal surface is just totally detached from the boundary. And they really bring home the point that this has nothing to do with asymptotics of ADS. So here's an example. This is the way the first island calculations were done. You have a black hole, it evaporates. If it's an asymptotically ADS, because we got so used to it, we put it there, I guess. We can imagine having a coupling at the boundary that extracts this radiation to an auxiliary system, and then we ask, after the page time, what is the entanglement wedge of this auxiliary system? And you find that you get a smaller generalized entropy if you include not only the auxiliary system, but also this island here inside the bulk, which is bounded by this quantum extremal surface. And you can derive famously the page curve from this calculation, but it didn't matter one little bit that this was an asymptotically ADS boundary. Now we can do this in asymptotically flat space as well. Out goes the radiation. And really, when we compute the entanglement wedge of this bath or auxiliary system, the only thing that matters about it is not what kind of system it is. What matters is that the radiation is there. It's the entanglement wedge of the radiation. And I'm sort of trying to lead you down a slippery slope here. once you realize that the island is in the entanglement wedge of the radiation, this should be true no matter where the radiation is. It shouldn't be important that you literally took it out of the space-time and put it into a non-gravitating bath. In the real world, you can't even think about doing that. And you know, we want Hawking radiation in the real world to obey the Page curve. We want it to be true that radiation that's coming out of a small black hole in our lab has an island inside the black hole. So if, for example, we had looked at the radiation right here, when it's in an asymptotic region, but not, so it's very weakly gravitating, it's just this dilute cloud, right? It's not yet in this auxiliary system. We would still want it to be true that, you know, its entropy follows the Page curve, and that happens because we get to include this island here. So the second lesson that I want to draw here is that it's not only not tied to ADS, it's not tied to asymptotic boundaries. There is such a notion as the entanglement wedge of the radiation, wherever it may be. So once we accept that, it becomes kind of confusing to ask, well, what exactly is this map? Well, we have some input that used to be some boundary region of the boundary of ADS, let's say, but we just convinced ourselves that's not general enough. And we want some output that's the entanglement wedge. What kind of map is this? And what I'll argue in this talk is that the correct choice of input region is really, we should allow any bulk region. Well, it could be that in the end we might be forced to restrict to certain classes of bulk regions, but I won't do that unless I'm really, I know I'm forced to do it, which I don't currently. So I will argue the input should be any bulk region. And that the way that we've been computing entanglement wedges until now should really be thought of as certain limits of that. Like if this bulk region happens to be in ADS and it happens to be really close to the boundary, then whatever prescription we find should reduce to the usual RT prescription or the appropriate generalizations to include quantum corrections and dynamics. And if we want to compute the entanglement wedge of an auxiliary system like this one here, which has no gravity, well, okay, so in the limit where you turn off gravity, our prescription, whatever it may be, should reduce to that. Okay. So I'll first, in the first part of the rest of my talk, I'll argue in a little bit more detail why, I'll sort of summarize these arguments and extend them a little bit, why I think bulk regions should have an entanglement wedge. And in the second part, I'll make a specific proposal, which is sort of analogous to the Ryutakenagi / FLM type of proposals in that it'll apply only in time reversal symmetric situations, roughly static situations. And I'll show that it satisfies some nice properties. So in the third part of the talk, I'll prove some of these if I end up having enough time left. Properties that we would associate with an entanglement wedge. So unless there are any questions, I'll get going. And do interrupt me. So yeah, so why should bulk regions have entanglement wedge? So I think I already said this, you know, it seems silly that we have to wait until the radiation has literally left the space-time before we get to ask about whether it has an island or not. I'd like it to be true that if I look at radiation that's really weakly gravitating and far away, that I should be able to compute an entanglement wedge for this region containing the radiation, and the output of whatever prescription that I'm going to be looking for should be that it's at least this region plus the island. I want, of course, the input region to be included in the entanglement wedge because we certainly have access to that. So that's one thing that we want to be true, right? Another good way of seeing that there's nothing wrong with considering bulk regions is to think of this tensor network pictures of how the bulk to boundary map works. Again, going back to ADS, where we have the most idea of how it works, but the goal here is to take some of the things we've learned about ADS-CFT and see if they can be made to work in arbitrary spacetimes. So in ADS, we've been drawing these these tensor networks, which, well, I should have maybe had another picture here of something like the happy tensor networks, where you see like there are lots of input legs, right? And then there's a network that sort of pushes the bulk input quantum state out to the boundary, right? But it's actually not that important that you push it all the way out to the boundary, right? You could stop earlier. It's a kind of flow, right, of the information. You could stop earlier and sort of harvest the state on a smaller circle, not quite out all the way out at the boundary. Or more generally, you can cut out some piece of the tensor network. These dots here are supposed to represent the dangling legs or the input legs, and these squares are random tensors, let's say, right? So in this situation, if I ask, can I read? So in this situation, I know, right, if these are random tensors, that given access to the green region, I can reconstruct this operator in the blue region. Yes.
Just to give you something to fight against. So the usual argument against this, which you're presumably going to dispense with, is that, for example, if you use the covariant entropy bound, that works for any surface, but usually it's an inequality. And similarly for tensor networks, if you pick an arbitrary region, then this kind of bound will just give you an inequality involving the entropy. And somehow the special thing about the extremal surfaces is that that's where the inequality is saturated.
Yeah.
So that's somehow that's the hill you have to climb, is to.
Right. So this is a kind of extremal surface given this green tensor network.
Yeah, but
so if I drawn a bigger tensor network, for example, right,
yeah,
then I could have drawn this blue surface to kind of go like this and maybe exclude some operators that I could have reconstructed if I wished.
Yeah.
And then I think that would.
But if you take an arbitrary tensor network with input legs and output legs, and you just draw some surface that grabs some of the tensors and not others, in general, it will not be true that the entropy is, equal to, the entropy is related to the area by inequality. There will be an inequality, right?
Well, what I have in mind here is that I've chosen a tensor network such that these are at least approximate isometries.
Yeah, but even something that's built out of a bunch of isometries, if you take a bunch of them, it might not be an isometry, right? Like if you do like even the happy thing, if you draw an arbitrary region where there are kind of too many legs going in and not enough legs coming out, right? Then it won't be an isometry, and then that's why you'll have an inequality.
Right. I think that's going to be taken care of by the prescription that I'll posit. Right now, I'm just trying to motivate searching for such a prescription in the first place. And here I was careful to make sure that there's one input leg and 3 output legs. And so we could have the 3 Qtrit code or something that does this for us, right? So that's right. But indeed, we're going to need a prescription that doesn't tell us that I can reconstruct regions where something like that isn't true, where I don't, where I don't have a chance of actually pushing the state into it. That's exactly the point. Yeah. Right. The next point is really just a fancier version, if you like, or, well, it's to say that not only do we not need to rely on these toy tensor networks, which are fun to think about and give us some intuition, but in fact, I think the picture is even clearer if we go back to the original rules for entanglement wedge, for what the entanglement wedge is in ADS, where it's best understood. And what I want to review here very briefly is this insight by Akers and Pennington from a while ago, that actually the original RT prescription is wrong even at leading order for some states. And I'm not that interested in these funny states that they considered, which are sort of incoherent superpositions of, let's say, a pure state of a gas and a maximally mixed state with, order 1 probabilities. These are funny states in that the von Neumann entropy is different from certain one-shot entropies. You can't compress them, and so there's really a big difference between trying to send many copies and then dividing by n, or just sending 1 copy. That's not actually my focus. My focus is that this forced them to consider a rewriting of the quantum extremal surface prescription Recall that we currently have two equivalent ways of sort of stating that prescription. One is the one by Engelhardt and Wald. You find the quantum extremal surface homologous to the boundary region with the smallest generalized entropy. The other one is the Maximin prescription by Aaron Wall, which is usually more convenient for actually proving things. Neither of them can be used in general because all of them involve in some way minimizing or finding stationary points of a quantity generalized entropy. Okay, that quantity doesn't appear in the criteria for what the entanglement wedge is when you have incompressible states. So, for example, what you would do, right? Or let me first tell you the rewriting of the criterion, right? So I think you'll all agree with me that if the blue surface is the correct quantum extremal surface for the boundary region B, right, then it is true that for any other homology surface in between blue and the boundary, that the area of this homology surface is bigger than the blue area by the amount of matter entropy, at least bigger than by the amount of matter entropy that's in between the two, right? If that wasn't true, then this would have been a better choice. Well, more precisely, you can then show that there should have been some other quantum extremal surface or minimal surface in between. So that's a funny way of thinking about this, but what really enters into the definition is not the difference between the entropy in these two regions together and the entropy just here, but a single quantity. So the difference between these two entropies will be what's called a conditional entropy, right? A conditional entropy is literally just some von Neumann entropy minus another von Neumann entropy, the von Neumann entropy of the whole thing minus the von Neumann entropy of A. If we could always express the relevant quantity in that way, then we could always find the quantum extremal surface by minimizing the generalized entropy, meaning minimizing the area and then separately the entropy. But we can't always do that because of the subtlety that Chris and Jeff pointed out. What really matters here is you need to compare the area difference to a certain conditional smooth min or max entropy, depending on what type of entanglement wedge you're interested in. And these smooth min or max conditional entropies cannot be expressed as the difference between two things. They can only be expressed as one thing that takes as input the two regions you're trying to compare. Because of that, they had to invent a new rule for what the quantum extremal surface should be. That's sort of analogous or equivalent in most cases to the quantum extremal surface prescription and to the Maximin prescription, but which can still be applied in these subtle cases. And the reason that I'm emphasizing this so much is that this new rule, I think, really encourages us to think of bulk regions further out, closer to the boundary, as being in some sense the recipients of information that sits deeper in the bulk. So let me illustrate this here. So what I've done, right, is I've illustrated some entanglement across the quantum extremal surface by these little blue wiggles, okay, or U's. That's supposed to illustrate that the vacuum is entangled across the surface, and the amount of this entanglement is measured by the area of the quantum extremal surface, right? Then I've put some matter into this region, and I've entangled this matter with a reference system that's external. Let me think of the left side of the space-time as another reference system that's really holding the purification of half of the vacuum on the right side. Okay, so basically everything on the right side here, there's a bunch of entropy on the right side, and on the left side I've included its purifications. Okay, and what I want you to think of is this area here as a resource. Like when you do quantum teleportation, for example, the amount of teleportation you can do depends on how many e-bits you and your friend share. By e-bits, I just mean bell pairs, right? And then when you send stuff, when you send stuff, you sort of burn up that resource. Of course, you also have to send classical bits, which we're not going to do here, but I still want you to think of this as a resource. Yeah.
Sorry, you didn't draw entanglement between, what is it, A prime or A prime and A?
You mean these two sides?
Yeah. So
yeah, I'm about to.
Okay.
Yeah. So that's what I'm going to use as a resource.
Okay.
So I'm going to ask, well, if let's think of this side as Bob and this side as Alice, right? If Bob and Alice share area of red surface many e-bits, then can they teleport Bob's state over to Alice? In other words, can they make it so that Alice now holds all these purifications of R and R prime that Bob currently holds? And the answer is yes, they can do that precisely if this is the minimal surface or quantum extremal surface. Then this can be done for any choice of intermediate homology surface, right? Because what I'm saying by saying that this is the minimal surface or the quantum extremal surface is I'm saying that this area plus this amount of entropy is less than that area. Right? So I can simply now take all of these entanglement lines and continue them over to just inside Alice's patch here. And there'll be enough room. I probably have some left over. Yeah.
Teleportations.
I'm not specifically talking about bit threads, so it'd be nice to connect that to that. Is that what you were asking about?
Yeah, I'm just saying that
Yeah.
if you draw another region like A prime, which is smaller than A, and another, and you keep doing the
Yeah, you can't think of it that
once you
way.
draw a bit thread at the end of the day.
So the
sequence.
correct thing is that this is the quantum extremal surface if and only if, for any choice of intermediate homology surface, I'm able to merge the state from Bob to Alice in this way. In other words, I can give Alice the purification of R and R prime with an amount of resource equal to this area. What is not true is that after I've done this, I can necessarily pick another homology surface even closer to B and repeat the process. Because this one might have an enormous amount of area, which I can then not fit into the next one. So that's a subtle distinction. What needs to be true is that I can, if this is the quantum extremal surface, means that I can pick any one intermediate surface and merge the state across it. It does not mean that I get to repeat the process. Maybe I can discuss this. It's not super important for what's to come. Yeah. So why do I tell you this story? I tell you this story because this makes very, I think, operational and sort of clear that what is really happening in this holographic map is that we're allowed to move the state that Bob holds closer to the boundary, as close as we like in this example, but it'll always end up in a bulk region. Right? This rule doesn't actually refer specifically to the boundary itself. It just says that you can pick any homology surface and move the state across it to the other side. Yeah.
But maybe I could. Someone. Okay.
But you just said that there is one surface where the area sort of maximizes between this surface and the bulk. Sorry, the boundary.
No, I didn't say that. There's no. There need not be a maximum.
So you could pick a arbitrary sort of surface.
I mean, I can just choose a surface that is like really wiggly like this, and then it'll have really large area, and then I can choose one which is not as wiggly further out, and it'll have smaller area. There's not a largest area necessarily in between.
Right. Right.
I think we're getting hung up on the same point that Bartek was asking about, which is an interesting exercise, but it's kind of, it's kind of peripheral.
It's kind of like if you can do it repeatedly.
It's a subtle detail in how you have to choose the prescription. My point here is that you can move the state out to a region that's closer to the boundary, any such region, but you're always just moving it out to another bulk region. Yeah.
Put another way, are you saying I can move it arbitrarily close or just close?
Arbitrarily close.
Okay.
Well, whatever that means. I mean, in the physical spacetime, there's always an infinite distance to go.
Sure.
So, but in this diagram, it would look close.
So I'll just ask a question with a 1-bit answer, which I think is correlated with Bartek's. So Bartek has this old story about how any curve in ADS can be given a state merging interpretation.
Uh-huh.
Is that like somehow a classical version of this?
I don't know, and I'll let Chris answer that if you would like in the discussion.
And maybe Bartek has an answer. I don't know.
I'm going to shut this down because I want to finish my talk. All right. So one thing that we want in a more general prescription is that if my input region A looks like this particular bulk region, it better be true that the output is the usual entanglement wedge of this boundary region. Okay, so that gives us another sort of data point or something to aim for. Okay, this is something we're going to want to be true. Okay, and my final motivation here is kind of after the fact, but I already alluded to this. We'll be able to show that the prescription that I'll propose here satisfies a bunch of sensible properties. The dumbest of which is that it contains the input region. That's not hard to arrange, but it will be shown to satisfy a bunch of things somewhat non-trivially, namely nesting, no cloning, and strong subjectivity. And I'll discuss this in a little more detail later on. And that's, I think, really where sort of, I think the support for this is coming from in my mind, that it obeys sensible properties. So let me tell you what the proposal is, again, in the static case. We're still kind of working on the time-dependent case. This is sort of the, again, this is the case analogous to the original RT proposal and its quantum refinement. Yeah. No, A is A is a codimension 1 in the space-time. So it's a bulk volume type thing. It's everything in the red line. Yeah, sorry, that's right. I didn't want to shade too many things, but A is everything inside the red line. So this is the prescription. Okay, so this doesn't have to be ADS now. This could be any space-time region. Let's say it's flat space. I don't know. So you look at your input region, and then you find the smallest region that the region that contains it with the smallest generalized entropy. Okay, that's all there is. Well, if the input region is attached to an asymptotic boundary, then you apply the usual homology constraint. In other words, the output region should contain the same piece of the asymptotic boundary of the spacetime. But notice that in this example, the input region is just entirely in the bulk. And this is a very simple example where the output is just sort of the convex hull of the input region. It doesn't always have to be like that. So here's an example where my input region consists of these 4 pieces. These 2 are so close together that I'm going to want to connect them and form their complex hull, because this will have less area than if I'd filled them in like that. But these 2 are so far apart from all the others that I'm just going to draw their own little convex hull that'll have the smaller area. Most of my examples here, just for simplicity, I'm going to choose examples where we only need to think about the area, not the generalized entropy. But everything I say really applies to this quantum corrected version. So we really want to minimize the generalized entropy.
Is this supposed to be covariant, or are you in a time symmetric slice?
As I just said, my prescription is for the time symmetric case,
Okay.
analogous to RT and
Okay.
FLM.
Right.
Yeah. And we are still working on the time-dependent version of that, which has been pretty painful. But you can ask me about it at the end. I can tell you what we have. So here's another example where I've drawn a spatial slice like this to illustrate that it has a bag of gold kind of geometry. I'm doing that because I can't really consider an evaporating black hole, given that I have a static restriction to these sort of static or time symmetric configurations. But this is time reflection symmetric. I could have some radiation, meaning just a bunch of particles in this region, which are entangled with particles in here. And so long as there's more of them, then the then this area in Planck units, then this input region A out here, this shell will have an island according to this prescription. So it does recover the island rule. Good. Any questions? That's it. That's the entire proposal. So any
A question.
Yeah.
I missed it. I mean, you motivated this by talking about one-shot quantities, and now you're not.
now I'm not.
Now you just have SGen.
Ah,
Sorry.
yeah, that's right. So I don't mean that actually. So the prescription that we give can easily be formulated in that language that Chris and Jeff invented in terms of these one-shot smooth conditional entropies. The reason I'm not doing that is that other than for motivation, it's not particularly useful to confuse you with that extra complication here. It was useful for me, at least I was hoping it'd be useful to say, look, when you really worry about the most general case, you're forced to adopt a version of the quantum extremal surface prescription, which in a very operational way tells you that you need to think of it in terms of, can you move the state out to some subregion of this bulk region that you started with? And that's kind of what we're now saying you should be able to do even when there's no boundary involved. But having obtained this motivation from their work, I'm now going to ignore their work entirely because it would just be really complicated and not add anything to my story to consider these funny states that are incompressible and for which you need this refinement. Does that?
Yeah, thanks.
Raphael, can I ask a question? Can you hear me?
Where?
Someone.
On
I'm
the-
online. I'm Xiaoliang.
You're online. Yeah, I can hear you.
Yeah.
Who are you?
I'm Xiaoliang Qi.
Okay, hi.
Hi. So if I apply this formula to the island case, then you will get not only the area of the island, but also the area of the original region itself.
Can you just
Right.
say that again loud and more slowly?
Sorry. Yeah. So if I apply it to the case of the island, like the case of the radiation you draw here, then your entropy will include not only the area of the island part, but also the area of the original region A itself, right?
Yeah, right now I'm not actually computing an entropy, but I think the idea would be that you say, yes, the true generalized entropy of this radiation region, which was always going to include these two areas, is actually somewhat lower than you might have naively thought because it includes the island. So there's an extra term that just goes along for the ride. So before you include the island and after you include the island, you have these additional terms coming from the boundaries of the bulk input region.
Okay, thanks.
Thanks, yeah. Great. Any other questions about this? Right now, I'm not even thinking of this as a prescription for computing an entropy. I mean, you can if you want, but right now I'm just looking for a way to get from an input region to an output region. Bigger than the input region.
Yeah, E of A is just a region, right? You haven't actually given us a
Exactly.
formula
I'm not
for
telling you
something
what
yet.
it means at all,
Yeah.
right? Because I don't know. What I can do is prove some stuff, unless there are further questions about the prescription itself. Okay, so because I said that E of A is the smallest generalized entropy region containing A, then trivially it contains A, so that much is fine. You can also show pretty quickly that, so notice notation-wise, I've given my new thing that takes bulk input regions the name E to distinguish it from the old thing, which is called EW, just so we're clear on the notation. It's important that E reduces to EW. So in a situation like this, right, where you have a region A, by the region A here, I mean this sort of outer layer that's close to the boundary region capital A. Now let's look at our old prescription. Our old prescription would have said this boundary region capital A has this entanglement wedge, the blue thing, okay? I want it to be true that if A has the conformal little a has the conformal boundary big A, and if A is contained in the old answer E of A, that, EW of A, that E of A agrees with EW. yeah, so you can think for 1 second about the definition, and you'll see that that's just the statement of the original RT or FLM prescription. It will. I mean, it's important that it be contained in it, because if A, for example, sticks out like this, then of course it can see more than the original entanglement wedge of this boundary region, simply because we put it in from the start. That's fine. It only has to reduce to the old prescription if it's actually entirely close to the boundary in some sense. Okay, these were the easy ones. Now, well, these are not particularly difficult to prove, but at least it's somewhat non-trivial. So no cloning. What do I mean by no cloning? So in the original QES prescription for boundary regions, right? It's important that if I can reconstruct an operator from some boundary region B, then I should have absolutely no information about that operator in the complementary boundary region, B bar or whatever, B prime, or else I could effectively do quantum cloning, right? I could pull the operator to two different systems, or I could pull the state to two different systems, and I could clone an unknown quantum state. That would be bad. Now, what's the analogous statement here that we're aiming for? It's actually sort of more important to explain the statement, I think, than the proof. The statement is that if the input regions A and B are suitably independent from one another, sort of analogous to complementary boundary regions, then it should be true that their entanglement wedges have no overlap. So we wouldn't want this to be true. And by suitably independent, what I mean, and this is a little bit more subtle than what we have to worry about in the boundary case. What I mean is that B, the input region B, is outside the entanglement wedge of A, and the input region A is outside the entanglement wedge of B. This is something we never have to worry about for boundary regions. They're always outside. But here that's important, because otherwise A and B were not really completely independent quantum systems to start with. And then this argument doesn't apply. So that's the assumption that each input region is outside of the entanglement wedge of the other, and then this is not supposed to happen. So suppose it did happen, that the entanglement wedges have an overlap region, then we can ask about the generalized entropy of E of A minus the overlap region. So imagine excluding this little middle bit, and E of B minus the overlap region. We can add them together, right? And then we can get the following inequality by thinking about just the geometry of these areas and ordinary strong subjectivity of the matter entropy. So when you think about it for 5 seconds, you realize that that sum is always less than the generalized entropy of E of A plus E of B. Okay. Yeah.
Regarding your previous point.
Great. In that case, let me finish the proof and then ask the question. So we've shown, or it's not hard to see, this inequality holds. But if this inequality holds, that means that either when I go from all of E of A to this slightly smaller region where I exclude the overlap, or when I go from E of B to the slightly smaller region where I exclude the overlap, the generalized entropy must decrease. Maybe in both cases it decreases. Otherwise, this inequality couldn't hold. Okay. So that means that at least one of these two entanglement wedges was the wrong answer, because it's supposed to be the smallest generalized entropy region containing A or B respectively. Right. So that's a contradiction, right? Unless the overlap region is actually empty, which is the thing we were trying to show. Now, yes.
Yes. Could you? I think you clarified it, but I missed your argument. Why can't we? What happens if we push little a, like the red line, beyond this this E of A? Like,
well, then you're gonna, in this, let's say it sort of sticks out like this.
yes.
Yeah, you're gonna probably want to connect it with two extremal surfaces like so.
Yeah, or let's say yes. I keep the anchors in I don't know how to pronounce that. The anchors, and I move A way beyond the E of A. Yes, for example, something like that. What happens in your perspective?
Then E of A is probably just equal to A. I mean, it depends on the details of the shape, but what's happening is that E of A can't be smaller than A by construction because A already has all the information about itself. So, I mean, both by our rule and by sort of, I think, any sensible requirement, A should be included in its own entanglement wedge. And so,
because you're showing inclusion, not that they are the same. No, you're showing. Well, okay, I'm sorry. I keep thinking about it, and then I ask you. Like,
okay. Any questions about this argument?
Yeah, can I just clarify, when you said that A and B have to be suitably independent? So I guess certainly
Yeah.
one part of suitably independent means that A should not intersect E of B and B should not intersect E of A.
That's the part that we're assuming.
Yeah, so that's the only thing you need to assume? Yeah,
That's the only thing I need to assume here.
yeah, I think you said that, but I'm just trying to make sure.
Yeah.
Yeah, okay. And
That's
so you say
right.
as long as
And
that's
the
true.
place where that assumption enters
Yeah,
is in the fact that when I remove from E of A this overlap region and make it
Yeah.
smaller to get this set,
uh-huh,
it still includes A.
yeah,
And that's important because later I make this argument that then, one of these could have been improved
uh-huh,
by shrinking it.
Yeah.
You could have decreased the generalized entropy by shrinking it. And that's only useful if after shrinking it, it still includes the input region.
yes, yes.
Thanks. Good. So then let's go to strong subjectivity. It's funny that nesting somehow comes at the end, but we first need to prove strong subjectivity. So this looks a little more complicated. And also Jeff didn't fix the letters in our figures yet, so I blame him for this. But alpha is A, beta is B, and so on. But yeah, so again, I don't want to make you like really add up areas and think about exactly how strong subjectivity is applied, but hopefully you'll believe me that so let's start on one end with the generalized entropy of the entanglement wedge of the union of A and B. So we first take the union of A and B. There's a subtlety to how you're supposed to take the union here, which I will only get into if somebody spots it. But in this example, it's not relevant. So you take the union of A and B, and you ask, what is its entanglement wedge? And let's say it's this thing here. Okay, so we connect them with these blue lines. That's the entanglement wedge of A union B. And then same thing for B and C. We take their union and then ask, what's the entanglement wedge? Smallest generalized entropy region containing them both. Let's say it's this one. Okay. Now what we want to show is, the goal is to show that the generalized entropy of these two things together, added up, is bigger than the generalized entropy of the entanglement wedge of B, which is not shown in this picture. Maybe it's something like this, plus the generalized entropy of the entanglement wedge of ABC, which is maybe something like, you add another line down here and take the whole thing. Okay, so that's the goal. How do you show this? In two steps. So first, you think about what happens when you exchange various surfaces and what additional surfaces might appear. You think about areas. That's what I mean by geometry. And you think about ordinary strong subjectivity. And those two things together tell you that our starting point, the sum of the generalized entropy of these two entanglement wedges, the one of A and B and the one of B and C, is bigger than the generalized entropy of their intersection plus the generalized entropy of their union. Okay. Then you observe that the intersection must contain B, because each of these guys must contain B. And you observe that the union of these entanglement wedges must contain A, B, and C, because it's the union of sets which contain A, B, and C. And therefore, both of these sets, this intersection and this union, were candidates that we could have examined as the entanglement wedge of B, or it would have been a candidate, this one here, for the entanglement wedge of ABC. The true entanglement wedge of B or of ABC can only have smaller generalized entropy than that, so we can continue the inequality and get what we want.
Raphael,
Yeah.
these need to be suitably independent?
Weirdly, no.
No.
Yeah. I mean, I wouldn't have died if we'd been forced to assume something like that, but we don't need to, so we don't.
Ah, okay.
Good. And the final one is nesting. Should be easier than it looks, but I don't know. So, but nesting is really just the obvious thing that if A is a subset of B, then the entanglement wedge of A should be a subset of the entanglement wedge of B. Okay, I sort of, well, if I give you a bigger input region, you should only be able to do better, right? You can't lose some information. Well, suppose that wasn't true. Suppose that we had a weird thing like this happening where the entanglement wedge of A contains a piece that's not in the entanglement wedge of B. Okay, well, one thing we know for sure is that A is in the intersection of the entanglement wedge of A and B, right? Because A is a subset of B and B is in E of B. And so from that, we can conclude that the entanglement wedge of A must have smaller generalized entropy than that intersection, or else that would have been a better choice, right? And it's also true, just more straightforwardly, that the entanglement wedge of B obviously has to have smaller generalized entropy than this other candidate here, which also includes B, E of A union E of B. So then again, you think about areas and you think about ordinary strong subjectivity, and you find that that actually implies a contradictory inequality. So add these two together, that gives you one inequality, but geometry of these areas in strong subjectivity implies the opposite. And so all of these have to be equalities. And I'm always assuming for simplicity, like the entanglement wedge is unique. In other words, you don't have some degeneracy. So then that forces you to conclude that the intersection of E of A and E of B is actually the same as E of A. In other words, E of A is indeed included in E of B as we had hoped. And that's the end of that proof, Bartik.
I'm probably not the only person in this room who dies to ask, are these generalized entropies going to obey monogamy of mutual information?
Oh, no, I think for the same reason that they don't for the same reason that they don't in ADS-CFT, right? I mean, I can always reduce this to the boundary region problem. And then if I have entropy in the bulk that violates that by enough, then it's right. This was always a statement just about areas, right? And it could be violated by the quantum corrections, in other words, the entropy of matter. So nothing changed here. This is just a more general thing than the usual prescription. So if it wasn't true in the usual prescription, it's not going to be true here. We have a mic.
A corrected version of that question is what happens if you assume monogamy in the bulk? I guess the answer is yes.
I guess a variation of the previous question is like, what happens if you assume
Yeah.
monogamy in the bulk?
I don't want to commit to that without
Okay.
having thought about it.
Okay, sure.
It's possible. We haven't. Yeah. The reason is that there are these new pieces of the area which have no analog in the original prescription, which is, the part of the input region that doesn't sort of pop out to include a bigger region. Like, think about, like in this example, just go back to here, right? There's a part of the input region area that contributes to the generalized entropy also of the entanglement wedge, and which has no analog in the case where you're computing the entanglement wedge of a boundary. In that case, there's sort of only that part that contributes. So that's why I don't know off the top of my head if it's true. It's a good question, thanks. Yeah, so that's actually all I have to say. Now, if we have time left, you can ask questions about what it all means if you really want to know. I just won't be able to answer them. But thanks.
More questions from the audience?
Raphael, can I ask another question?
Yeah.
Can you hear me? Yeah. So when we have the boundary region, then this entanglement wedge, degree of freedom in the entanglement wedge of the bulk is mapped
If we,
to
sorry, if we have the boundary
boundary.
region, then the entanglement wedge, what?
So there is a encoding of the bulk degree of freedom to the boundary.
Right.
So here there is no boundary. Then is the proposal that there's some bulk degree of freedom in EA is mapped to the boundary of EA, or is it boundary of A or bulk of A? That's
Yeah. So my intuition is, first of all, I should, if it's not already obvious, I should stress that all we've done here is defined a map. We've not defined a quantum gravity theory or a specific dictionary. We've just sort of said there should be some sense in which information in a larger region can be stored in a smaller one. And I think the best sense that I can make of that is this picture, right? So what we're doing already in ordinary ADS-CFT is we have the capability of merging the state across any intermediate homology surface, in the sense that what we're really doing, right, is there are two reference systems, R and R prime, and the purification of those reference systems used to be at least partially in the region between the red and the blue surface. And if this is the correct quantum extremal surface, then that area here provides enough resource that you can basically extend these entanglement lines and move the purification of both R and R prime to just inside this surface. Now, when you think about what this would actually mean, if this was a process where at the beginning, the state looked like this, and at the end, the state looked like that, notice that this process would have erased this space-time region. Right? We've completely destroyed the vacuum both here and there. This is no longer a good, this is no longer a good region. So all that we're saying is there is enough room on the boundary of this input region A to move all of the information about the entanglement wedge just inside A. I don't claim that there's an observer here who can force this to happen. I have no idea, maybe. But whatever the process would be, it's not some standard effective field theory process, because you're really required to access degrees of freedom all the way to the Planck scale to make use of this full entanglement resource at this surface. Or in the language of tensor networks, you have to access the in-plane legs and treat them as actual degrees of freedom. So that's going to destroy the vacuum right here. I don't know how much that helps. It's a little bit analogous to, if you go back to ADS-CFT and you have, let's say, the t=0 global slice of the CFT, right? I can look at the state of that slice. I can act with an operator so that it adds a particle in the middle of the bulk. But that process has no bulk interpretation, or more precisely, has no bulk interpretation in the Wheeler-DeWitt patch of that boundary slice. It doesn't even satisfy the Bianchi identities or something, right? You're changing the energy like locally in the middle of the bulk. What it I think should really be thought of is as a complete destruction of the bulk and a rebuilding with that particle in it. So I don't think this is a completely unparalleled idea, but again, here, this process where I move this purification of R and R prime into the region A would have the effect of destroying this space-time region.
All right, I think one last question, then we got to go on to Arvind.
So it seems if you fix little a, you get some EFA, and you can obviously vary small a to make it larger within EFA, and EFA will stay fixed, if I understand correctly.
I didn't quite understand.
So if you have some little a,
yeah,
you get some EFA from your prescription.
Yeah.
You can enlarge little a.
You can make EFA bigger. Yeah, the nesting implies that the new entanglement wedge will at least be as big as the old one.
Right, and so long as it stays within EFA, EFA will be unchanged.
Yeah,
is that correct?
That's right.
So is there a notion of smallest little a? keeping. the
Yeah, that's a
EFA?
really good question. That's right. Yeah, it might be. So that's at least an interesting exercise, is to ask, how much can you shrink little a without shrinking its entanglement wedge? And in examples like this is fairly obvious, right? So here, the only thing about A that's really important is this outer boundary of it, right? And so I could have just used that. In the covariant case, it might turn out that we will have to. I think it's more likely than not that we won't, but it's possible that we may have to restrict A in some way, for example, by that kind of shrinking procedure. But I don't have anything more to say about it right now.
All right, let's thank Raphael again and move on to Arvind.